Alrighty, hey AP Chemists, here is part 3 of your summer work. This is the first video lecture. We'll be talking about chemical bonds and chemical formulas. So there are going to be two major types of chemical bonds that we're going to look at the beginning here. Another vocab word that I'm going to throw here when we think about chemical bonds, like actual bonds between atoms, is a word called intramolecular, and we'll call them intermolecular forces. Not to be confused with something called intermolecular, and that'll be during the school year. All right, so chemical bonds form between the attractions of positive and negatively charged particles. So I have a couple of drawing, and I kind of already wrote on some of the notes here to kind of save lecture time so you don't have to watch me write everything. So bonds happen between the attractions of protons and electrons. Remember that charged particles exert forces, like attractive and electrostatic forces. Like charges repel, and opposite charges attract. So when we have charges in compounds, we'll have something called ionic bonds. This tends to happen between metals and nonmetals. So I'm over here now. All right, so ionic bonds happen typically between a metal and a nonmetal. And you're going to have to look back at previous lectures about where are metals found on the periodic table, left side of the periodic table, where are nonmetals on the right side. Now this happens when charges form. And if you remember from the previous lectures, metals tend to lose electrons and nonmetals tend to gain electrons. So when they come into contact with each other, when a metal comes into contact with a nonmetal, the metal will lose an electron to the nonmetal gaining an electron. These oppositely charged ions attract one another to form an ionic bond. So here's just a quick little example. And I also put another vocab word over here, something called valence electrons. We'll learn about that more during the school year. Valence electrons are these electrons that are gained and lost by atoms. They are the electrons involved in bonding. So it's very important to know that vocab word during the school year. I wanted to introduce it here and you could write that down. So here's just a quick example between sodium Na and chlorine or chloride Cl. Sodium has this one electron that it wants to get rid of. Chlorine has 7 electrons, these valence electrons that it has, and it's going to want one more. It's going to want to take this electron. So, boom, chlorine's going to take this one electron, and it's going to become this negatively charged ion now that it has gained an electron. So I put a -1 there. And then since sodium lost that electron to chlorine, it becomes a positively charged ion. And if you remember vocab, a positively charged ion is a cation, a negatively charged ion is an anion. And this becomes the sodium chloride ionic compound. And there is a beautiful colored diagram here for you to see that exchange here between sodium atoms and chlorine gas. There's another major type of bond called covalent bonds. This typically happens between two nonmetals. Instead of this gaining and losing of electrons, the bonding atoms tend to share some of their electrons. So there's a sharing of electrons between two atoms. So if I had two chlorine atoms kind of coming together, I'm going to just quickly draw them. These dots here are electrons. Instead of one gaining and losing, these two atoms are going to come together and they're going to share some electrons together. And so now I have two chlorine atoms that have come together sharing electrons, and they form a covalent, or what we also call a molecular compound. So two nonmetals coming together, we call that a covalent bond, the bond that it makes, and that is identified as a molecular compound. And I kind of drew on the side here for you too. Here's just a periodic table. I want to remind you that on the right side of the periodic table, that's where most of our nonmetals are. So things like nitrogen, oxygen, sulfur, iodine, silicon, fluorine, bromine, carbon, those are all nonmetals. And then here are a bunch of compounds that contain two different nonmetals. They're all considered molecular compounds. You're going to have to be able to just quickly identify things as ionic and molecular, especially for your exercises here. And that'll be very important in the school year, where you have to quickly identify a compound as ionic and molecular and then talk about its properties. All right, now let's end this lecture here with just representing compounds, chemical formulas, and molecular models. So the best way to represent a compound is with a chemical formula. So right here I have water which is H2O. So water, which is represented as H2O, I'm going to draw it. It also looks like this, and we'll talk about that in a bit. In H2O, there are 2 hydrogens and 1 oxygen. So in H2O, I have 2 hydrogens, 1 oxygen. That's 3 atoms in total. Let's see how I could identify that in a compound. Well, in a compound, I see I have these capital letters. These are the element symbols. Each element symbol represents each element that's in a compound. And then in the bottom here, it looks like I have, and you're not going to see one right here. I'm going to leave this blank for right now. We have something called subscripts. I'm not going to write all this down, but you could write this as a little note for yourself. Subscripts tell me how many of each atom there are in a compound. So I have 2 hydrogen atoms in this compound. And since I don't have a number here next to the O, we pretend and assume that there's a 1 there. If there is no subscript, assume that it is 1. We don't typically write 1. Don't typically write 1. We don't write, like kind of like 1x or x to the first. We don't write that. We just assume that it's there. Let's look at types of chemical formulas now. We have something called an empirical formula, and I did write the definitions here, so you could pause and write the definitions and listen. You could try and quickly do it around while I do it. So an empirical formula is the simplest relative number of atoms in a formula, meaning I cannot divide them further. The ratio or the numbers that I have in that formula cannot be divided by a common multiple or a common factor, so I do have a simple formula. So here are just 2 examples here. I have C4H8O. I'm going to use the subscripts here. I have 4 C's, I have 8 H's, and I have 1 O, oxygen. 4 to 8 to 1 cannot be divided further. If it was 4 and 8 alone, yes, that could be divided further, but 4 to 8 to 1 cannot be divided further. That is an empirical formula. Altogether, there are 13 atoms in this formula. Methane, CH4, that has 1 C. Remember, there's no subscript I see for C, for carbon, so I assume it's 1. And there are 4 H's. That's 5 atoms in total. I add up all of those subscripts together. That cannot be divided further, so that is an empirical formula. A molecular formula is the actual number of atoms in a compound, but it's a whole number larger than an empirical formula. And I'm going to do it using the examples on top here. So for example, if I were to multiply all of these subscripts by 2, I would get C8H16O2. This would be considered a molecular formula, and as you guessed it, all of these can be divided by a common factor. They all have a common multiple of 2. If I divide all of them by 2, I'll end up with my empirical formula of C4H8O. But I just wanted to do that as an example there. This is an example of a molecular formula. The subscripts can be divided by a number that they all have in common. I'll do the same thing with methane here, CH4. Let's say I multiplied it by, 5. If I multiply each atom by 5, I'll get C5, and then 4 times 5, H20. This is a molecular formula. Both 5 and 20 can be divided by this same number of 5 to get our empirical formula, CH4. You're going to have to be able to recognize empirical and molecular formulas in your practice, so make sure you're able to get that here now. And in the future, you're going to have to be able to recognize things as empirical and molecular to identify them to do other things. Then, of course, we have structural formulas. Typically, we represent these formulas with lines. Those lines represent bonds. So this line right here are bonds. This could be blown out a little bit more. Like, look, here's methane again. By the way, all of these are the same compound on the left and right. Here are the 4 bonds in methane. There are 4 bonds in methane, carbon-hydrogen bonds. Okay? We could also use molecular models, which are like circles or spheres to represent atoms. So again, here we have, let's just say this black circle is carbon. Let's say this is hydrogen. This would have 1 carbon, 4 hydrogens. This would be the ball and stick model for CH4. We could also use space filling model where we don't have these lines, where they're all just connected as circles, kind of connected together. This is also CH4. You could see 1 black circle carbon and then 4 of these white circle hydrogens right here. So just wanted to show you different ways to represent compounds. I'm going to end with just looking at examples of representing formulas and then lead you to your practice here. So here are just some examples. Like here's benzene. The molecular formula of benzene is C6H6. And here's what the structural formula looks like. And here's what its ball and stick and space filling model would look like. It has 6 carbons, 6 hydrogens. That is a molecular formula because that 6 and 6 can be simplified by dividing by 6. If I divide both 6's by 6, I get C1H1, and this would be its empirical formula. This has 1 carbon, 1 hydrogen, that's 2 atoms total. C6H6 has 6 carbons, 6 hydrogens, that's 12 atoms total. I'll look at another one. Let's look at glucose, something that you might be familiar with in biology or just in life. Glucose is C6H12O6 that has 6 carbons, 12 hydrogens, 6 oxygens. Altogether, that's 24 atoms. What am I going to divide that by to get my empirical formula of CH2O? I'm going to divide that by 6. They all have a common number of 6. And so if I divide 6 by 6 and 12 by 6 and 6 by 6, I get 1 H2 and O. So 1 carbon, 2 hydrogen, 1 oxygen. That has a total of 2, 3, 4 atoms. And again, look, that kind of works out that I divide by 6 and I have a 1/6 of the number of atoms. So now, to end this little lecture here, you're going to do these 3 exercises here. I did give you some answers to get you going. For question 1 exercise, you're going to determine the number of each type of atom in the formula. I gave you the answer to D. It's 11 atoms. You could work backwards to figure out that's 11. For number 2, you're going to have to identify empirical formulas, and I did make a note here. Some of these may already be empirical, so don't be fooled by that. Like D is already empirical. 5 and 12 cannot be divided further. There is no common number to divide them both by, so D is already an empirical formula. And then finally, with exercise 3, you're going to have to look at the formula and identify them as either ionic or molecular. Remember, ionic would be metal and nonmetal. And remember, molecular would be 2 nonmetals. And I did the answer to D here. S and O are 2 nonmetals, so that would be a molecular formula. Alrighty, to complete this lecture, you are just going to turn in the answers or your answers to exercises 1 through 3. If you have any questions or concerns, feel free to reach out to me on the Remind or an email.